So sampling methods are actually quite a general approach to do various things in machine learning and also in statistics and also in physics, in fact. Very generally, a sampling can be considered how do we choose or do we select a certain number of measurements from a population. It could be that you're analysing some data and you've got to pick certain pieces of data out of there, maybe at random, in order to get a representative set of data that you can then say something about and make hypotheses about. Have I got enough data? This is also when you're running experiments. Effectively, you're sampling the sort of the universe of all possible things that you could have done and all vast different numbers of people that could have done a task. You have a certain set of people that's doing the task, and then can you then make some hypotheses on the basis of that? Quite often sampling methods are used to help you do computations which are otherwise intractable and can't be done, especially the ones involving things like sums and integrals. So it's a general purpose and fairly easy thing to do, but it can be very, very slow and is generally a lot slower than deterministic methods where you know precisely what you're doing. There's no element of chance in a deterministic method. And it can be very difficult to get a representative and good samples. I shan't say too much about exactly what all this means on this particular slide, just to say that, sampling methods can be very useful for doing things like calculating expectations when you're actually multiplying the probability of a sample against the value and then integrating it out. The important thing with a lot of these things is sampling can be used to end up with an estimate, say, of a expectation, and you don't actually have the samples as such as part of the process being a result of the mechanism. You're really interested in the result of something like an expectation, and this is particularly what we'll see when we look at actually importance sampling, because in importance sampling, as we'll see, you can use the fact that you're weighting the importance of samples, but you never actually see the samples as such. So lots of applications for these things in machine learning. This is the expectation maximization algorithm in making predictions in if you like, doing calculations in certain Bayesian calculations and model comparison techniques. We're not going to talk about these things in the course, but just to let you know that that's the sort of thing that you can use these things for. Sort of techniques that use this sort of approach of sampling random things goes under the term Monte Carlo methods quite a lot, because it sort of gives you the indication that there's some randomness there. Just like the famous casino at Monte Carlo involves a certain amount of probability that you're going to do things. And these methods can be useful to calculate stuff. So, for example, we could calculate the sample mean of something for IID data. So IID refers to the fact that we've got a data source which leads to independent and identically distributed samples. So in fact, RAND, for example, in MATLAB is IID. We always get the same underlying distribution coming from it, and all the samples are independent. And we can sample from these things in this random way in order to come up with calculations. In fact, when we're actually sampling from RAND and then we're calculating the mean, we are effectively using this kind of approach. So Monte Carlo is an unbiased estimator, and generally speaking, the important thing to notice is, as we've seen already, your estimate basically gets better as we have more and more samples. So if you're doing the mean, say, you're sampling from a RAND n or something, the more samples you get, the closer you get back as a good estimate of what the actual underlying mean, for example, was. And it generally goes down with the square root, 1 over the square root of the number of samples. Obviously, it's quite easy to calculate the mean. All we have to do is we add up all the values and divide by the number of them, right? And that would be a Monte Carlo maybe way of doing something like that from something like a RAND function. We can use Monte Carlo methods to estimate things as well. For example, this is just an example really for estimating pi using a Monte Carlo method. So the way this works is, in this particular case, we know the area of a circle is pi r squared, right? So if we have a circle of area of radius 1, then the area is going to be pi. Now the bounding square around this is going to be, obviously it's 2 radiuses up and 2 radiuses across, right? So it's going to be 2 by 2, it's going to be 4. So the ratio of the area of the circle is going to be, ratio of the area of the circle to the area of the square is going to be pi, which is the area of the circle, divided by 4, which is going to be the area of the square. So we've got this ratio of the two things as pi by 4. Okay, so there's our radius. So obviously the diameter is 2 radii. So the square has got a larger area than actually the circle has, of course, because we've got these extra little bits at the edges which are not basically where the circle is. Now what we could do, as an example of using a Monte Carlo method, let's imagine we can easily sample from this 2-dimensional space of the square, which is quite an easy thing to do. All we have to do then is, we randomly sample points which are 2-dimensional, which fit in this square, and we look at how many points we've got coming in, and we look at how many times they fall within the circle, right? Then we can calculate the ratio. So the ratio of the area is going to be approximately given by the samples inside the circle divided by the samples inside the square, and we know that that equals pi by 4 in this particular case. So if we actually run this, we can say pi is equal to 4 times samples inside the circle divided by samples inside the square, right? It's easy to calculate that. So we could run this experiment. We can sample from this 2 by 2 area, because it's just a 2-dimensional thing rather than a 1-dimensional thing, and we just count the samples up that fall within, which I've plotted here in red, and we plot obviously we also record the number of total ones, and we're plotting the ones outside the circle in blue. As you increase the numbers, what we'll see is we get a better and better estimate of pi. So we're calculating the estimate of pi, like I said we were going to do, by this ratio. Here, when we've got we've got 10 samples, and it's already saying pi is about 3.2. We've got up to 100 samples, and it says pi is now 3.112. It's getting a bit closer. If we do a substantially increased number, is that 1 million samples, then we get in 3.141, blah blah blah. This is not quite there yet. You can see that it's starting to get to a value which we would consider to be a very basic but reasonable estimate of pi. And this is just using a Monte Carlo method, right? And how do we actually do this? Well, what we've got to do in our code, first of all, we've got to be able to sample from this 2 by 2 area, and then we've got to be able to say, is a sample within the circle or is it outside the circle, right? So what we need to do is we need to write a function telling us, are we inside the circle? So basically, is the value smaller than the radius, right? Is it within the circle? And if so, then we're within the circle. So we just have to look at the value and just check the boundaries, if you like. I'm not going to talk about the detail. You can work that yourself. So what I'm going to do is, for all the points, I'm just going to look and see whether or not they are basically within a radius of the center point, and in which case they're within the circle, or whether or not they're actually within the square as well. If you set the boundaries up on the sampling, you wouldn't have to do this calculation. You just assume all of the points are in the square. And then all we have to do, right, we just run this thing for a certain number of samples. I'm running it for 10,000. Here we're sampling over the range that we need to do in order to get within the square. We then calculate the number of points within the circle, calculate the number of points within the square, and then we calculate our estimate of pi as 4 times the number of points, basically, or in this fact we're just calculating the mean number of points within the circle divided by the mean number within the number inside the square, and then we just plot it out. That was a very basic way of actually doing an estimate using this sort of random method, just showing that you can use these methods sometimes to do some useful calculations. So importance sampling is a bit like this. So again, importance sampling differs from rejection sampling in an important way. The big problem with rejection sampling, as we've already mentioned, is it throws away some of the samples, right? Because it's got to throw things away in order to end up with the samples looking like they're coming from the desired distribution and not the one you're actually sampling from. Now, rather than throwing stuff away, we've got an alternative, and we can call, well, basically it's called importance sampling, and it doesn't throw samples away. Actually, it just weights them. So the important thing about this kind of sampling is it doesn't lead to you having samples from the distribution, but what it can do is it lets you weight a sample as if it was coming from the desired distribution, and this is useful if you're doing calculations with things. So when you're computing things like integrals using a sampling method, then importance sampling can actually let you use all the samples, but what you do is you don't just use the value of the sample, you weight it so it's appropriate for the distribution you're actually interested in. Right? So you don't actually get samples from this method, but you can do calculations with this method. Right. So again, importance sampling, we can't often then draw from an arbitrary distribution, we know that, and so what we do is we put on a distribution across the target one that we can actually sample from, that fits in the range, and we've already talked about that. Now, but this time what we do is we don't throw anything away, we just re-weight the value. So rather than throwing them away with a probability relating to the ratio of the probability of the actual target to the probability of the scaled, if you like, distribution we can actually sample from. What we do is we re-weight the values of the samples by this ratio px over qx. And then when we're doing calculations, we just, rather than using the actual sample that we got from our candidate, what we do is we use it, but we scale its value first, so it looks as if the contribution it's making is coming from the target. So imagine we're doing some calculation. This could be an expectation. So expectations we'll see a little bit later on. In a continuous form, basically you're integrating the probability of something happening with its value across all of its values, right? We have to calculate this integral. You can also do it as a sum if you have discrete values. And what we need to do, right, is now we can say, well, actually we can slightly change this function and say, well, let's say we can't directly sample from P of x, but we can sample from Q of x. So let's put in a couple of Q of x terms in here instead. So we can just write P of x divided by Q of x multiplied by Q of x. As you can see, the denominator term here and the top term here, they would normally cancel out. So this is actually the same thing in terms of value as this integral here. But then what we do is we can now sample from Q of x, right, rather than sampling from P of x. But then we've got this scaling factor in front of it instead. That's basically the idea. And this is basically the same as if you're doing a discrete example as well. What we have is, as we have our function and we're just multiplying by a scaling factor for this value now, rather than actually using directly the value. So we have a weighting factor in importance sampling rather than throwing things away, right? So we just weight the actual corresponding contribution from a sample. And like I said, as long as we're doing it in a calculation, that's perfectly fine. Obviously, Q and X and P of X must have some basic functions. We want them to be, less than infinity. If Q of X goes to 0, then we've got a problem, right? And what it's basically doing, it's just re-weighting the importance of the samples. That's all it's doing, and hence the name of the technique.